So in this question here, it seems like we have a tank, like so, with a pipe coming out the end and filled with water. And it comes out the pipe. Pipe is always full. The pipe is always full. So they're referring to this section here as always full. What gives the change in kinetic energy and gravitational potential energy of the water as the water flows down the pipe? So let's look at this as the individual water molecules. So let's say there's these individual water molecules. Like so. Now, so we're asked about the kinetic energy and the gravitational potential energy. And what we can definitely see will happen, there could be no doubt about the fact that the height is changing, delta z. So the gravitational potential energy must decrease. So that means any place where it increases must be taken out. So we're at 50-50 right away. And then when we look at the choices, the kinetic energy either remains constant or it increases. So for it to increase, the velocity would have to increase. And for the kinetic energy to remain the same, the velocity would have to be constant. So which of those two things is happening? Are the water molecules going faster and faster as they shoot out that tube, or are they traveling at a constant speed throughout? Now, it stands to reason that this question is tricky because we think the gravitational energy must be converted to kinetic energy. But let's think logically now about what happens to a particle if it's traveling faster. If the particles are indeed accelerating as they go down here. So here's my red water molecules, like so. If they are accelerating, then that means that the particles down here are traveling faster than the ones up here, and these are slower. Which means they must necessarily be spreading apart. They must necessarily be spreading apart from each other. If each of these particles, 1, 2, 3, 4, 5, 6, 7, if the farther down the tube you've been accelerating longer, they're getting faster, then what that means is 7 is traveling faster than 6, and 6 is traveling faster than 5, and 5 and 4, and 4 and 3, and 3 and 2, and 2 and 1, and certainly 7 than 1. If 7 is traveling faster than 1, it must be traveling farther, which means there must be space must open up. Must open up between them, between the water molecules. It would be like creating a vacuum of sorts. And we are told that the pipe is always full of water. So what that must mean then is for this to happen is that the velocity must stay constant. And if the velocity is constant, that means that the kinetic energy will stay constant. It's a non-intuitive situation, and that's because the water must stay in contact with each other as it's going through the tube to be filled up. So that's why it is choice A. And my suspicion is that most folks will quickly jump to C, saying this is a simple conservation of energy. So if what we have happening is a change in gravitational potential energy, the gravitational potential energy is decreasing, the energy must be increasing in some other way. And so there is linear translational kinetic energy. There is also something we haven't learned about yet. It's called rotational kinetic energy, in which that energy gets involved in the spinning, the revolving and the revolution of those particles. And so that energy must then be translated into some kind of additional rotational kinetic energy. And that's this question.